Hi. If you don't know, I am a PhD student, but I'm almost done. I'm looking at postdocs, plan to be graduated soon. And in this very long video, the longest on my channel by far, I am going to be using AI to try and teach myself some freaky math. So to explain that a little bit, what this is, so I'm using this website, MathHub. This is launched by the Honest Torus, a fellow mathematics YouTuber. Someone on his team reached out to me and was like, hey, we will give you some free tokens for the website. So tokens that's the thing that you purchase, and then you use those tokens to access various features on the website. So they said, we'll give you some tokens if you, do a review for us. And I said, cool, that sounds cool. So that's basically what this is. And the whole 2 hours, whatever plus of what you see, well, except for the end where I give my final review. So you can skip there now if you want. But other than that, the real meat and potatoes of this video is me teaching myself two different subjects. So it's sort of broken into two parts. There's a bunch of, timestamps below so you can navigate through those. I do think if you sit and follow along with me learning, you might learn some stuff about those subjects too. So it could possibly be helpful in that regard. But also, just to let you know, so what are the topics? The first one was, well, basically about equivalences of derived categories. And the other one was about the inverse Galois problem. Probably if you're just going to watch one of them, that's the more interesting one, I would say. But also what I'm doing there's long stretches of time where I'm just sort of waiting for the thing to load. So I end up reading random PDFs online. And so that's all in there too. And you can navigate through that. So part of it, you'll see when I'm interacting with MathHub and when I'm just reading random PDFs online. So I kind of do both. In the derived category bit, there's little bits where I'm just sitting there picking locks while I wait. So it's all fast forwarded and it just goes, and that's what's, that those little parts. So anyways, if you're still here listening to me yap, you can just jump ahead to the end. But if you love me and you want me to be rich forever, watch the whole video and all the ads that come with it. Yeah. So I'll see you at the end then, I guess. Okay, so this is actually attempt number 3 of reviewing MathHub. We had some technical difficulties, as I guess the site was getting popular. I think it was something to do with that. But we're back. Allegedly, everything should be working now. Let's check it out. So we got to start a new course. I think I'm going to do it a little different than the original thing I'd put. So I'm going to put equivalences, maybe like derived, Morita, equivalence, and causal duality. That's what I want to learn about. So that's what I'll say the topic is. Primary goal, main outcome. I would like to be able to understand, to better understand causal duality in the very long term. I want to see how this arises in the categorical local Langlands program. But for now, just understanding basic examples is fine. Since I know it's related, I would also like to understand when two rings have equivalent derived categories of modules. Let's try that. I don't have a reference image. So my secondary objective is to get more comfortable with working with derived categories, I guess, and including possibly DG and DG categories and infinity categories, because I know that could intersect with this, but I don't know. Maybe that's I don't know if that should be in there. Yeah, maybe that's it. Maybe I could say that. How am I going to apply this? I would like to be able to prove that certain algebras in my research are causal dual to each other. Let's say that. Let's go thorough review. Let's go thorough proof level of detail. Prior exposure. I have been to a summer school on causal duality in category O. I guess that's basically it, right? What else can I say? I'm familiar with the basics of derived categories and ordinary Morita theory, shall we say. Known weaknesses. What do I put here? There are many, but I'm trying to think what are known weaknesses relevant to this that I could say. Maybe I could say more comfort with derived categories. Like, I don't know. It says optional. I'm gonna leave it blank for now. So I want to make sure I have tokens to check out other lesson plans. So I think this will be enough. My course plan is now generating. Will it be finitely generated, like my modules? Oh, wow, right as I say it. Here we go. Okay. Review of basic derived categories, triangulated categories and properties, review of ordinary Morita theory, intro to derived Morita equivalence, maybe compute derived functors and examples. Yeah. Maybe I need less of the background. Definitely all this later stuff looks good. This looks like a good plan. Wow, even suggesting infinity categories and enhancements. Okay. Sure. I don't need quite as much review at the start. Let's see. Maybe we could begin maybe we can begin with derived Morita equivalence. Let's adjust. I would even suggest explore Langlands at a basic level. Okay, did it adjust already? I don't know. Let's start course. I don't think it adjusted, but that's fine. Sometimes, very rarely actually, do I ever pick locks on my free time. But these ones, normally when you're picking a lock, you need to put in a tension rod, and then you pick. You put the tension rod and you put this pick in here, and that's what actually picks the lock. But these cheap locks that you get for like the lock room from Dollarama or whatever are so cheap that I don't even need to pick it. It just pops right open. Let me show you. Here's another one. Right? Here's another one. They're locked. It's definitely locked. And look at this. I just put it in. Boom. Popped. Like absolutely nothing. So yeah, think about that next time you're going to lock stuff in the change room or whatever. These locks mean nothing. Okay, so that took a little while, but okay, not bad. 5 minutes or whatever it was. In order to invent the whole course. So let's dive right in. Let's jump over to session 5. Introduction to derived Morita equivalence. Here we go. Okay. Welcome to session 5. Derived Morita equivalence was generalized as classical Morita equivalence by working in the derived category rather than the module category. So this notion captures deeper homological relationships. Yeah. For instance, a hereditary algebra, I forget what that means, and it's tilted algebra often exhibit this phenomenon. Then I guess it makes sense that a key motivation comes from tilting theory. Certain special complexes called tilting complexes induce such derived equivalences. In favorable cases, okay. Next up, we'll explore precise criteria for when a tilting module yields a derived equivalence. Okay. Well, let's see. What is a tilting module slash complex? Complex. I wonder how much we can ask it within one lesson. Can I just keep asking it within this lesson forever? Could I ask all of the rest of my questions? Just ask the whole rest of the course in this session. I will say at this juncture, the speed is maybe not great. But maybe I should ask it more serious questions, right? Because if I did something like if I just Google tilting complex, right, and looked it up from Wikipedia, like boom, I'm reading stuff faster. But you could argue that this is still a good way to maybe use this alongside MathHub. Tilting theory describes a way to relate module categories of two algebras using so-called tilting modules and associated tilting functors. Oh, Bernstein and Gelfand. Oh, interesting. These functors were reformulated. Okay. Let's see. What do we got? Anything here yet? No. Suppose that A is a finite dimensional algebra. A right module is called a tilting module if I vaguely recall this. T is projective dimension at most 1. In other words, it is a quotient of a projective module by a projective submodule. Its self-extensions are 0, and the right A module A is the kernel of a surjective morphism between finite direct sums of direct summands of T. Okay, that one's a little weird. I'm going to need some explaining for that. Given such a module, we can define the endomorphism algebra, which is another finite dimensional algebra, and T is a finitely generated left B module. The tilting functors, Hom from T, X from T, tensor, and tor relate the category of A modules, a finitely generated right A modules to the category of finitely generated right B modules. Okay. That makes sense. MathHub is still thinking. In practice, one often considers hereditary finite dimensional algebras. Let's go look up that word, because the module categories over such algebras are fairly well understood. The endomorphism algebra of a tilting module over a hereditary finite dimensional algebra. Okay, whoa. Let me say it again. The endomorphism algebra of a tilting module, so that was B in the above, of a hereditary finite dimensional algebra is called a tilted algebra. Okay. That makes sense. And what's a hereditary ring? Especially if all submodules of projective modules are again projective. Holy smokes. I mean, fields, right? Basically fields. For a non-commutative ring, left. Okay, well, I guess we know what hereditary is. Oh, let's look at examples. Let's see. I wonder, do I need to stay on this page for it to load? I wonder. Let's look at the examples, then we'll stay on the page. Semi-simple rings are left and right hereditary. By a similar token, von Neumann regular rings, I don't know what those are. Semi-simple rings are hereditary. What do we got here? For any non-zero element in a domain. They're introducing all these other words I don't know. Commutative hereditary domain is Dedekind. Oh. Okay. So that is a nice big swath of examples. An important swath of examples there. Okay, I'm happy with that. Okay, let's see. This little brain's thinking still. Okay, I'm going to see if I can pick this lock before we get an answer. Oh, here we go. We got an answer. Never mind. That's what I gotta do. I just gotta threaten to start picking the lock, apparently. Great question. A tilting module. Well, we just finished reading it, but okay. A tilting module over a ring R is a finitely generated module satisfying these properties. This is as finite, but often one in classical cases. Okay, I guess it's believable that we could, I guess it's believable that we'd want higher ones. There exists an exact sequence where Ti is a finite direct sum of summands of T. Oh, that starts with R. Interesting. I actually like this way of expressing it better than Wikipedia says, because now I can understand this sentence. These conditions ensure that T behaves like a derived generator of the module category. Okay. A tilting complex generalizes this to the derived category is a bounded complex of finitely generated projective R modules, such that the derived HOMs are 0, so no self-extensions in the derived category. The smallest triangulated subcategory containing this and closed under direct summands is the entire category. Okay, so that means it generates it. When such a tilting complex exists, Rickard's theorem guarantees that R and this and the endomorphism things are derived Morita equivalent. Okay. Cool. I wonder if I should ask it for the proof of Rickard's theorem. In the special case where R is hereditary, a path algebra of a quiver without oriented cycles. Oh, for example, any classical tilting module automatically gives rise to a tilting complex concentrated in degree 0. Aha. Here's a quick example. Okay, nice. If R is the quiver from 1 to 2, then the module P1 and P2, where P1 is the indecomposable projective at vertex 1, and S2 is the simple, P1, S2, I see, is the simple at vertex 2, is a tilting module. Its endomorphism ring is the path algebra of the quiver of the opposite quiver, and R and RT are derived equivalent, but not classically Morita equivalent. Very interesting. Now to connect this to our session above, why does the tilting module induce an equivalence? I was going to ask this. The key lies in the vanishing of the higher x and the generation condition, which together ensure that the derived functor is an equivalence. We'll prove this criterion rigorously next, but first, can you see why the generation condition rules out degenerate cases where T is too small to capture that? I probably shouldn't do this at night when I'm tired. Now to connect this session, why does this tilting module induce a derived equivalence? But first, can you see why the generation condition rules out degenerate cases where T is too small to capture this? So what would be going wrong here? Degenerate cases where T is too small? I don't know what that means, actually. Where T is too small? The generation condition. Oh, that's this last one. Okay, so we need to rule out a case. Yeah, I'm not sure at all, actually. Sorry, I'm not sure I can see why. Perhaps it would help perhaps it would help if we went through a detailed example with proof for some such specific ring. I feel like I worded that kind of weird. It's probably going to have to think for a little bit. Let's see. I mean, what if we just go to Google? What am I looking for? Detailed proof of derived equivalence via a tilting complex. No, I don't think I want to read this archive paper. Maybe I do want to read that. Derived categories and tilting. Let's let's look at these random notes. Review the basic definitions of derived categories and derived functors. Morita theory. Let's go jump over to 20. I think that's where we want to be. Yeah, kind of looks like it. Rickard's theorem. Nice. Okay, let's see. It's MathHub. Okay. MathHub has generated something for us. Oh, no. This is still the old thing. Okay. Let K be a commutative ring. One version of the Morita theorem states for two K algebras, the following statements are equivalent. There is... oh, right. Ordinary Morita equivalence. So K-linear... a K-linear equivalence between categories, always given by tensor product. There's a finitely generated projective B module, which generates this. Yeah. This form of the Morita theorem carries over to the context of derived categories. The following theorem is due to Rickard. A direct proof can be found. Oh, so we're not going to see a proof in here? Let A and B be K algebras which are flat as modules over K. Is that a big ask? I mean, I know we like flat algebras, but is that a big ask? Then there is a complex of AB modules such that the total left-derived functor of the tensor product is an equivalence. That makes sense. Equivalently, there's a complex of modules such that the following conditions hold. T is perfect. I forgot what that means. Perfect complex. Is an object in the derived category of A modules. The perfect complex of modules over a commutative ring is an object in the derived category of A modules that is quasi-isomorphic to a bounded complex of finite projective A modules. Okay. We're still thinking. T generates D mod B as a triangulated category with infinite direct sums. Sure. And we have this vanishing X condition. Condition B in 2 means that D, the derived category, coincides with its smallest strictly full triangulated subcategory stable under forming arbitrary coproducts. Right, that's what we mean by that. The implication from 2 to 1 is clear, is it? Oh, yes, of course it is. To prove the implication 1 from 3, so supposing we have 3, 1 puts, from 1 to 3. 1, if we define FA, okay, right, so that should be, T should be a complex? FA, right. Is that necessarily projective, though? I guess maybe it has to. A should be a projective complex in its module category. Okay. It looks like it's generated something for us now, so let's take a look. No, this looks like... Oh, it just timed out. Okay. Notes and feedback. So we'll generate this for me to look at later. Okay. I guess we'll keep reading color. Since F is... let's just cancel. Let's just cancel and move on. Okay, let's go back to learn. Courses. My courses. Zero to 14 lessons. I thought we did lesson 5. Oh, continue? Are we not? How do we finish the lesson? Okay, what's next? Oh, wait, this is the example. There is an example here. There is something different going on here. There is something different going on here. Okay, let's take a look at this. Absolutely. Okay, let's work through a concrete example in detail to see exactly how the generation condition ensures the tilting module captures the entire derived category, and why, without it, we might miss essential objects. So we take the hereditary algebra of this quiver, and recall that the indecomposable right R modules, being the projective at vertex 1 with composition series top S. Right. What does this mean? Socle. Right. So that's like the maximum submodule or something like that. So it sits in a short exact sequence with S1 as the quotient and S2 is the kernel, I guess. And P2 is simple and projective at vertex 2, and S1, yeah, S1 is this quotient. Okay. And consider this module. So first we have to verify its tilting. R is hereditary, so we know this immediately. Indeed, P1 is projective, and S2 is also projective. So there we go. Vanishing extensions. If we compute, so to compute X, since all summands are projective, X1 of everything? All summands? All summands of what? Wait a second. What was t? T is this sum. Oh, right. Yeah. Okay, sure. Yeah. Yeah, I agree. Okay, generation condition. So we need an exact sequence here with I don't know what that notation means. Recall that R is equal to this, which is equal to this, which is equal to T. Oh, R is equal to T? So we can take this. Oh, okay, that's easy enough. Which trivially satisfies this condition. Thus, T is a tilting module. Okay. So we compute the endomorphism ring. Right, so it should be, what, 3 copies of K, I guess? Right, so as a matrix ring, S is going to be... oh, well, I guess this this matrix with values, lower triangular matrix with values in K. Which is allegedly the opposite quiver. Okay, which it did say previously. Thus, the path algebra. Thus, S is the path algebra of the opposite quiver. Okay, now we need to show that these are Morita equivalent. Because T is a tilting module over hereditary algebra, it gives rise to a tilting complex concentrated in degree 0. By Rickard's theorem, derived equivalence follows. But we're just pushing things back to Rickard's theorem, but I want to know why it's true. Okay. Okay, let's see. It gives rise to a tilting complex concentrated in degree 0. Derived equivalence follows if T generates this. But why? How do we get an equivalence of derived categories? Is what I want to know. I don't see what the equivalence is. How do we take complexes in one case and go to the other? The generation condition ensures that R is in the category generated by T. Since R generates the whole thing, then the category generated by T has to be the whole thing, right? Okay, I agree. That part makes sense to me. Concretely, without the generation condition, suppose we took T prime to be S2 alone, then those things are true, but there is no exact sequence starting with R, only using copies of S2, because S2 cannot map onto P1 or generate the summand P1 of R. Why is that a problem, though? Okay. So T prime would only contain complexes supported at vertex 2. What does that mean? I guess maybe I do need to better understand some of the background. Can you please remind me of the definition of the category? Oh, I guess we can use tech. That's not the right way to tech it, but generated by T. When does the lesson end, though? By forcing T to be large enough. Okay.
Oh, here's how the derived equivalence is implemented. It's implemented by taking rhom from T, and that should wind up in the derived category of S. It's not clear to me that it lands in there, but which is an equivalence because T is a compact generator with no self-extensions. Yeah, that's not clear to me. Can you verify that S1 is not in the module category of S, but does appear in the derived category of S as the cone of a map between projectives? This shows why derived equivalence is weaker and more flexible than classical Morita equivalence. But S1, I mean, S1's a simple module, so how could it arise? How could it arise as the cone of something in S? If it's not in the module category of S, I guess we gotta wait. We could go back over to color. Yeah. So where were we here? Since F is a triangle equivalence, it is then enough to check the analogs of A, B, and C hold for the object A of D mod. Properties A and C are clear. So A is a perfect complex. I guess these things are all preserved under triangulated equivalences. And C, I would say this isn't exactly clear to me, but maybe I shouldn't have skipped all the background. And then we just need to check B, I guess. Checking property B is non-trivial. Okay, and then we have a citation. The hard part of the proof is the implication from 3 to 2. Indeed, motivated by the proof of the classical Morita theorem, we'd like to put x equals to t. The first problem is that although t acts on A as an object in the derived category, it does not act on the individual components of t, so that t is not a complex of bimodules as required in 2. We refer elsewhere to a solution of this problem. Okay. So it does look like there's a lot of background reading to be done here. Okay, well, I think I'm going to end the session for today because it's been about a bit of time. First thoughts. Oh, there's live learning. Why don't we see that? I think these are the YouTube videos. Advanced theory of the symmetric group. Yeah. Well, I think that's where I'll end it for now. And we will come back to this. We will come back to this later, I guess, in the same episode. I'm going to try making a different course with maybe a simpler topic, and see how that goes. Okay, time for a different lesson. We're going to try out a different lesson here. Just to, see how it handles different things. So I'm going to spare you the trouble of me, the boring part, this time of me filling stuff in. And we are going to look at the inverse Galois problem, as you can see here. So I've decided, yeah, I basically just asked it, like, oh, I want to understand, the inverse Galois problem. What does it mean? And, like, what are some cases that we know? I said, let's focus on the actual big one, like over the rational numbers, but, in the sort of secondary goals, I said stuff like, let's, we could take some time to understand it over other fields like p-adics or whatever. So it's given me this basic description of it. So I don't know what to say. Cool. So what is today's lesson then? Maybe I'll tell it, maybe I'll say, yeah, okay, I'll just say that, and then I'll see what it says. I guess I should try to, I still did not pick the most easiest basic thing, I guess, but I still should try to act like, or pretend like, oh, there's more that it said. Oh, I didn't scroll down. Okay. Oopsie daisy. This is called the inverse problem because classical Galois problem starts with polynomial S first group. And in this case, we're asking, oh, maybe I haven't explained it to you guys. Maybe you read it on the screen, but yeah. The inverse Galois problem, all this is saying is for every finite group, does there exist an extension of the rational numbers whose Galois group is isomorphic to that. So a key tool in the Galois correspondence, which sets up a bijection between intermediate fields of the extension and subgroups of this. The IGP essentially asks whether this correspondence is surjective onto the class. Yeah, if all finite groups. Okay, and it even mentions some cases. It probably asked me a question I should have talked about then. A key tool in, where are we here? So we already know some positive cases. For example, Kronecker-Weber theorem tells us every finite abelian group is realizable over Q. Right? Cyclotomic fields. And then we get this thing, which is abelian. But then, of course, we can look at, by the Galois correspondence, we can look at subgroups and quotients of this thing, and just choosing n appropriately, you can make any finite abelian group show up in there. But what about non-abelian groups? For instance, a symmetric group is realizable. It's the splitting group of this. And, of course, famously, A5 is realizable, quite famously as the Galois group of a quintic polynomial, which says that you can't find a solution in radicals. Next up, what does this mean? Partial? The statement was unable to be formalized in lean form. Oh, okay, that's cool. That's cool. Oh, I didn't realize this before. This tells you, like, whoa, okay. That is pretty cool, actually. I will say that is cool. That is crazy. Maybe I should be using this to learn lean. But here we are. We're still thinking about the next thing. So next up, we'll examine how specific groups are realized in practice and review the Galois theoretic machinery that makes such constructions possible. Okay. So again, we're waiting. Known cases of reincarnation? Whoa. Not what I was going for, but I am very interested. How are we claiming there's known cases of reincarnation? Wow, 20 cases suggestive of reincarnation. Okay, well this is now we're on a crazy tangent. Let's get back to math. Known cases of the inverse Galois problem. Let's see. Has AI answered us yet? Okay. We already got the next one, and it's all verified. Great question. Today's focus. Blah blah blah. Two main goals. We've already touched on the statement, but the real intrigue lies in the contrast between what we can do and what remains out of reach. For instance, we got all the finite abelian groups. What about the non-abelian case? Okay. To build intuition, consider this polynomial. It's irreducible by Eisenstein's criterion. Hell yeah, baby. We love Eisenstein. And then we have this degree 6 extension, S3, yep. What makes this possible? It hinges on two Galois theoretic ideas we'll reinforce today. Irreducibility ensures the Galois group acts transitively on the roots, and the Galois correspondence links field extensions to group structure. So constructing extensions with the desired symmetries is equivalent to engineering groups with specific properties. Okie doke. As we move forward, we'll see that realizing more complicated groups requires deeper techniques. Hell yeah, modular forms, baby. I want to hear about that. Here's a question to ponder. Why might irreducibility of a polynomial be necessary but not sufficient for its Galois group to be the full symmetric group? Think about what additional conditions would force the group to be as large as possible. Actually, that's a good one. I should be able to answer this question immediately. I taught a course on Galois theory. But I guess I've been thinking about different things since then. I mean, I could go back and look up the theorems, but why might irreducibility of a polynomial be necessary to have Galois group Sn? Well, I mean, that's kind of weird. I mean, what does that even mean? I mean, well, if you define the Galois group, oh, well, we need a transitive action, and if it were reducible, we would have different orbits, right? So if the polynomial was reducible, the Galois group would would it necessarily have different orbit? I think it would. Yeah. I'm pretty sure it would. I'm losing my mind. Yeah, because it has to preserve the minimal polynomial or whatever. So yeah, if it were reducible, the Galois group would have more than one orbit. Wait a second. Is that problematic though? Is that problematic? You could have Sn acting. Think about it. What additional conditions would force the group to be as large as possible? Why does a polynomial have to be irreducible? Okay, well, let me just say this. I'm tempted to say, because in the irreducible case, it is transitive. No. Yes. But yeah, I'm tempted to say it has something to do with the transitivity of the Galois group on group on the roots, but I'm not sure. I guess, right. If n has to be the degree of the polynomial, do you mean that the n in Sn is the degree of the polynomial in question? Let's try that. Let's try that and see what it has to say. I was going to think for a bit. So we'll see. Maybe I'll do, I was thinking about doing a post comparison, but let me just see if we go Claude AI, Claude WC. Perhaps that's who we should be asking. Maybe we could compare if it's quicker to just go through Claude. Yes, access it all, baby. I agree to everything, I guess. My date of birth. When was K-theory tutoring born? I guess we should probably tell Claude we're how about 01 2001. Let's say that. Whoa. Use Claude for free. Okay, let's see. Nothing here. I understand. K-theory. What should we call you? Call me K-theory. What are you into, K-theory? Learning and studying. Find patterns in my research. I guess that's what we're doing. No, wait, that's not what we're doing. I'm going to ask it something else. Okay. Boo, boo, boo. Actually, scrap that. Let's talk about the inverse Galois problem. Can you please explain to me the proofs of some cases? Can we perhaps realizing all symmetric groups? Perhaps realizing all symmetric groups. Let's see what Claude has to say there. Okay, let's go back. Let's check. We're still thinking. Happy to explain how we realize symmetric groups as Galois groups. We want to show for any n there's such an extension here. And the strategy is going to be, of course, we want a degree n polynomial where the coefficients are independent transcendentals over Q. I don't think that's true, though. I don't think that's true. Well, I guess that's maybe, this is why it's thinking, and it's verifying things in lean. Because then we won't get nonsense statements like that. Splitting field construction. Let K be the splitting field over this. Well, wait a second. But how do we know that we can choose such coefficients yet? Okay, let's let Claude cook and see what happens. They're definitely not transcendental, though. Any automorphism of K fixing F must permute those roots. So the Galois group embeds into Sn. Yes. But crucially, any permutation of the roots can be extended. But that's not true. Why this works? The generic polynomial? But we didn't use the generic polynomial. This said general. Okay. Well, let us see now. Now our Math Hub has loaded. We were right, says Math Hub, anyways, to connect irreducibility with transitivity, and yes, the n in Sn is indeed the degree of the polynomial. Great intuition. Let's clarify. This is irreducible of degree n, then its Galois group acts transitively. That's a key consequence of irreducibility. However, transitivity alone doesn't guarantee the full symmetric group, of course. So what else do we need to force the Galois group to be all of Sn? One powerful criterion involves discriminants and cycle types. Actually, yes, part of the proof is coming back to me now. I got distracted by some tape on my wall. If the discriminant is not a square, then the Galois group is not contained in here. In addition, if the Galois group contains a transposition, yeah, so this is actually what's coming back to me now is that I remember proving this by constructing, basically just by showing certain kinds of permutations that are known to generate the symmetric group are in there, building polynomials that make that happen. If, in addition, the Galois group contains a transposition, reducing modulo prime, factors linear terms, and also now something's coming back to me about these theorems about the mod P behavior controlling things in the Galois group. This is why irreducibility is necessary, but not sufficient. So we consider x to the 4 plus 1. It's irreducible. But this is a root of unity, so of course its Galois group's going to be abelian. Right, Klein 4 group. No transpositions appear. Partial. Okay, so what was confirmed and what was not? Let's see. Come on. Here we go. Unable to be formalized in lean at the moment. Okay. So, what feature of the factorization of a polynomial modulo a prime tells us that its Galois group contains a transposition? Let's go back and read that again. If, in addition, the Galois group contains a transposition, for example, by reducing modulo a prime, where f factors is a linear term, times an irreducible of degree n minus 1, what feature of factorization modulo prime? Is it that it has a linear factor? Seems like what it said. Gotta remember my dummet and foot. Or a Luffy. When I taught the course, we worked out of a Luffy, which I love, but I guess one downside is I think dummet and foot actually did the mod P splitting polynomial thing. That doesn't seem quite right. Your argument didn't seem to depend on any specifics of the chosen polynomial. Another thing we could do, let's also compare, so the inverse Galois problem PDF. Let's just compare this to clicking random PDFs and see where we get. Sorry about the moving of the mic there. Some lecture notes from 23 on archive. I like that. The inverse problem for p-adic fields. This is a cool paper. Definitely been meaning to jump into it on one of my live streams or something. The Hilbertian property, and how dare you not put respect on the man's name with a capital H. So MathHub's still loading. Claude gave us an instant answer, but it might not be right. The real approach. Yes, we do need to pick a specific polynomial. Thank you. A concrete construction. Is this gonna work though? Because isn't this famously... Oh, maybe the signs are different. I was gonna say maybe this is famously the polynomial that has A5. Okay. Additionally, the rigorous general argument uses Hilbert irreducibility theorem. Can you please give me the detailed proof? So we're still thinking here in the study of Galois theory. Yeah, so how does this compare if we just go start reading a random PDF? This looks great. It's only 10 pages long. I guess we'll want a larger source, a longer source. A large number of realizations. Oh, this is an interesting paragraph. Of groups as Galois groups can easily be found using basic types of extensions. For instance, using cyclotomic field extensions and the theorem of finitely generated abelian groups, one finds that every abelian group can be realized. We also have that if K and K prime are two Galois extensions of a field with empty intersection, then KK prime will realize the product group. Yeah, that's nice. Although I don't think what's unclear there is that we can use that to always say if we have two groups then we get a product, right? This is like contingent on some extra conditions. I do wonder. Okay, let's see. Is MathHub generated yet? No. Okay, so with a little bit of prompting, I think Claude is giving us most of the details of the proof now. We have this field and these indeterminates. Let these be the roots. I'm still not so sure about this. I mean, this is towards the right idea, I think, to be using this theory of indeterminates, but okay, well, let's see. Let's let Claude cook. By construction, these are elementary symmetric functions. Wait, when did you say that? When did you say that? You never said that. It is piecing together the right proof, kind of, but okay. So let's go back here. What was I saying? So it's that it has a linear factor. I'm on the right track. Having linear factor modulo prime is only part of the story, but to guarantee a transposition of the Galois group, we typically need the polynomial to factor modulo some prime as a product of a linear term and an irreducible factor. Okay. That's what I meant. But, okay, maybe I could have been more precise in how I stated that. The factorization pattern corresponds via the Frobenius element to a permutation with the cycle type, which is an n-1 cycle, not a transposition. Okay. For a transposition, we usually look for a prime where the polynomial factors as a quadratic and a bunch of single ones. Okay. But here's an elegant shortcut for degree n polynomials. Hell yeah. If the Galois group is transitive, which comes from irreducibility, and contains a transposition, then it must be the full symmetric group. Nice. This is a classic group theoretic fact. Yes. This is how I recall it going. Let's look at a concrete success story. I love that wording. Success story. The symmetric group is realizable over S4 is realizable over Q. For instance, this polynomial is irreducible, has non-squared discriminant, and modulo 2 it factors as this. Is that what we wanted, though? It gives us a 3-cycle. So modulo 2 gives us a 3-cycle, I see. And then modulo 3, we get a double transposition. With a bit more analysis, one can confirm. Okay, so it kind of gives up there. But fair. I don't know. Maybe if it was me lecturing to some student who came in and asked me a question in office hours, I'd be like, well, yeah. This illustrates the general strategy to realize symmetric groups who combine irreducibility, discriminant checks, and modular factorizations. Okay. Next, we'll see how even more exotic groups, like the simple group of order 168, can be realized. Showing this isn't just about solvable or abelian groups. Great. Let's see that then. So put that in there. Let's see what Claude says. So thanks. What about the proof that we can realize PSL to 7? And, well, this random PDF is very interesting. Would probably be a good place to go read. And probably has some modern results. But let's also just try a simple regular Google search. Proof that PSL 27 is a Galois group over Q. I bet you anything that actually Keith Conrad has some great notes on this. Yeah. Oh, there's a paper. There's a big paper that shows. There's a paper here that talks about a whole bunch of them. Various polynomials. So we just go look at the actual paper. Let's see. Math Hub. Still thinking. Claude, what do you got? Great question. Klein's quartic curve. How the hell we can use Klein's quartic curve? That's pretty cool. Okay, that doesn't help us, Claude. Function field approach. Work with function fields. Okay, but how? How? Explicit polynomial realization. Yes. Can be realized as a permutation group. What do you mean by that? Constructing resolvent. I believe there are explicit polynomials known, but they're quite complicated. The smallest degree faithful representation of this is degree 7, so we need at least a degree 7 polynomial. Why? Let's ask, why does having smallest faithful representation degree 7 imply that the polynomial needs to be degree 7? Oh, I guess, I mean, No, actually, I that makes sense, right? Because the Galois group is acting on the extension as a Q vector space. So it should act on that linearly. So we should be getting a representation of the Galois group on that field, right? That's realized over the rationals. Um, and so, yeah, yeah. And does it have to be faithful? Does it have to be faithful? That's not so clear. No, maybe it does. Maybe it does, because it's like, yeah. Because if there's some automorphism that and acted like the identity, it would just be the identity. So it does have to be faithful. Okay, so I think I understand that, actually. Math Hub still thinking. Let's accept all cookies. Well, let's ask it. Can you please explain the rigidity method in more detail? We describe a technique for determining the set transitivity of the Galois group of polynomial with the rationals. As an application, we give a short proof that this polynomial has PSL 27. Nice. Okay, cool. Let's maybe download that. Okay, we'll just look at it here. Oh, view PDF. What's that? Let's click that one. Nice. Okay. It's an open question. Yeah, we know. Show me the meat and potatoes. Here's the method. Okay, it looks a little complicated. But let's read it. Let P of X be a monic polynomial of degree greater than 1 with these zeros. Consider these. Then these fields are equal. Whoa, wait. What is B1 up to Bm? What is B1 up to Bm? Oh, those are sums of distinct elements. Are the sums taken R at a time? Okay, to be fair, Fisher, Urbach, and McKay are probably, generally speaking, better writers and smarter than I am. But I would argue that that is not very clear. That's not very clear what they mean. Well, Math Hub is loaded. So, no problem. Moving on from that question, let's dive right in. The key idea is... Wait, what was their question? I've been bouncing around too much. For PSL 27. The key idea is when you reduce polynomial modulo p, where p doesn't divide the discriminant, the way it factors tells you about the cycle type of some element in the Galois group. That's Dedekind's theorem. Right. So if it factors into those, and the Galois group contains an element whose cycle decomposition has those lengths. Okay. So where the lengths of which cycles? Those are the degrees, lengths of the degrees. Okay. So to detect the transposition, you need a factorization that includes exactly one irreducible quadratic factor and the rest linear. But what is that? Right. Yes, exactly. Yeah. Right. Combining this with irreducibility. Okay, I feel like. Yeah, but you already told us that though. You already told us that. Why can't we use the same strategy to realize every finite group? What might go wrong if we try to, say, construct the quaternion group as a Galois group? None of these were analyzed. I guess we're moving beyond what Lean has done or can do at this point. Yeah, that's fair. What I meant to ask was if you could explain the proof that we can realize PSL 27 as a Galois group. But I guess we should try and answer the follow-up question. Why can't we use the same strategy to realize every finite group? Well, certainly, it's not just a matter of having the transposition. Now, the quaternion group, of course, embeds in a symmetric group. But to answer your question, I would guess that the quaternion group does not embed into a symmetric group of the appropriate size? Question mark? No, actually what I just said probably doesn't make that much sense. The rigidity method. The idea is to realize a finite group as a Galois group of the branched covering of the Riemann sphere. Aha. So we're doing some algebraic geometry. Trying to use étal fundamental groups here. So we take a branch covering of the sphere with these branch points. Take a loop that goes around each one of them. This covering gives us the monodromy homomorphism, where n is the degree of the covering. Okay. If we let G be a finite group, let these be the conjugacy classes, a generating system of this type is a tuple where we choose one from each conjugacy class and whose product is 1, and where they generate the group. Okay, so this is only going to work for pretty specific groups. The set of all generating systems forms a union of braid orbits. I don't know what those are. Oh, orbits under simultaneous conjugation preserving the product condition. Rigidity. The tuple is called rigid if there is exactly one braid orbit of generating systems. Okay. If G is rigid generating system of this type, then G can be realized as a Galois group. Over this, and by Hilbert irreducibility over that, right? I mean, I guess we should probably review that idea. I should probably review that idea. Any generating system gives a branch cover with that monodromy. Okay, I mean, I guess this gives us the idea for PSL. Oh, let's see, is MathHub loaded yet? No. With conjugacy classes. Okay, so I guess the trick is that we gotta do some stuff to understand why we have such a generating system in PSL 27. I guess we just got to do some matrix analysis, basically. Okay, but I mean, that's a nice overview. It's not bad for an overview, but we want details. Okay, let's go back to these guys' paper. For r equals 1, the result is trivial. Oh, okay. We can illustrate. Okay, so that's it. It's these two lemmas, and then we basically have it. Okay. I'm a little confused about what they're writing, but maybe if we skim over this and come back, it'll make more sense. Degree M, whose zeros are the Bj. If the Galois group is the alternating group, then this is an irreducible polynomial. Okay. This follows? How does this follow? Let's check. Math Hub, still thinking. G has to land in between these two things, okay? The discriminant of the trinomial is easy to calculate. Since this is a square, we know that G is a subgroup of A7, right? General result. On the other hand, P of X is irreducible over Q by Eisenstein's criterion using 11. So G contains a 7 cycle. Is that true? Does that follow immediately? Oh, because I guess maybe... Does that tell us about the mod 11 irreducibility? And then that's what gives us the 7 cycle? Furthermore, the Sturm sequence shows that this has exactly 3 real roots. So complex conjugation is a permutation of the cycle type. But PSL is the only proper subgroup of these containing elements of those two cycle types. Okay. I don't know what the Sturm sequence is, so definitely using some fancy technology to get there. But okay. I mean, at this point, we know that there's something to do with rigidity, right? So we could just try googling that. Rigidity inverse Galois problem. Okay. Now we've got a whole 58 pages. This is what I'm talking about. Math Hub still thinking. The inverse Galois problem asks for which finite groups occur as Galois group. Oh yeah, okay. This is the introduction. We know this stuff. We're pros at this stuff at this point. Should we jump over right to Riemann? Let's do it. Yeah. How do we find the Galois group? Okay, this just tells us an example of finding the Galois group. Riemann's existence theorem. This is one of the foundations on which rigidity is built. Eventually, it will ensure the existence of a field extension of Cx, the complex function field whose Galois group is G, where G satisfies some specific conditions. It is based on coverings of the punctioned Riemann sphere, and this chapter begins by setting up the relevant background in algebraic topology. It goes on to explore Galois coverings, and it ends with the proof of the topological version of the theorem. Okie dokie. But Math Hub is loaded. I do feel like it's maybe going a bit faster than last time. But also, maybe it's just not as late in the day, and I'm just not as tired. Okay, so I asked if it could explain PSL 27 as a Galois group, but I now realize by doing Googling that's probably going to take a bit of work. Great question. Let's clarify a subtle point you raised. The quaternion group, well, I ignored my PSL2. Oh, no, okay, it's going to talk about there. It does embed to a symmetric group. Yes, I agree. It faithfully embeds into S8. I didn't know S8 was... Is that the smallest faithful one? It's got to embed in a smaller one faithfully, no? I mean, perhaps not. The real issue is more arithmetic. This cannot be realized as a Galois group over Q. So that is false. Because the inverse Galois problem is open. The inverse Galois problem is open. So this would say that it's wouldn't this say that it's false? I think you made a mistake if Q8 couldn't be realized as a Galois group over the rationals, then wouldn't that mean the IGP is false? But let's see what it had to say about the other stuff. But shout out to Brouwer groups. Followers of my channel will know that I've been talking about Brouwer groups a lot. Now, about PSL27. This is celebrated early success in the inverse Galois problem. It's a non-abelian simple group. We can even use this very simple polynomial. Hit it up with Eisenstein. Mod 2 reduction shows irreducibility. Discriminant is a square, so it's an A7. So this is the argument Claude was giving us. And then applying Dedekind's theorem to some small primes. Wow, mod 3? Wait. Huh? This can't be right. Mod 3, it is definitely not congruent to X7 mod 3. This term disappears, but this is -1. So this is definitely not correct either. I should have included that in my message. Factors as a product of a linear and an irreducible sextic, yielding a 6-cycle. But no. Mod 5, it factors as a cubic and an irreducible quartic, giving this permutation. And then it claims that these cycle types generate a subgroup. But I think the thing that's missing from that, and what I think is missing from Claude, is how do we know that those are the only cycle types that show up? Like, do we make an argument that for higher primes it stays irreducible or something? In fact, this group, yes, okay. It does mention rigidity, so that's cool. Key takeaway, realizing this requires more than just checking cycle types. Okay. But it often uses geometric or representation theoretic methods. But the existence of such polynomials, sure, okay. Verified, wait, it even says verified? Wait a second. Sure, every finite group embeds into a symmetric group, yeah. If polynomial over Q is irreducible modulo prime, then it is irreducible over Q? Wait a second. No. No. Wait. That doesn't smell right to me. That doesn't smell right to me. Did this? Let's see. If a polynomial is irreducible modulo a prime, is it irreducible over Q? Am I crazy? No, yeah. Does not guarantee, yeah. What? I mean, yeah. So this polynomial, irreducible over Q. Well, this AI overview probably isn't going to be right. Because, yeah, this AI got the implication wrong. Just because there is a prime where it isn't irreducible is not the same as just asking for a prime by saying if there is one prime for which it's irreducible. If you can find a prime for which mod p it's irreducible, then the whole thing is irreducible. But I still find this claim dubious. Okay, so this person lists a couple strategies. Let's see. Yeah, but I still think I wonder if I can even cook up a counterexample on my own here. Like wait a second. No, maybe it is right. Maybe I'm losing my mind because right. Wait a second. What are we saying? So exists P such that this is irreducible implies this is irreducible. Well, we could take the contrapositive, which would say f of x reducible implies for all p this is reducible. And yes, of course, that is true. Okay, so it was right. I'm just stupid. That's not true. Don't say things like that about yourself, Kristaps. You make mistakes in public and you put them on YouTube forever, but you're not stupid. For a separable polynomial, if it has discriminant a square in Q, then it's Galois group. Sure. This polynomial, sure. Okay, so those claims are all verified, but I still think it made those mistakes. What time did we start yapping today, by the way? 4:43, so I've almost been yapping for an hour. Oh, okay. Do we have an answer now? Excellent question. You're right to scrutinize this. The inverse Galois problem asks whether every finite group can be realized as a Galois group of some extension over Q. It is still open. Aha. So if someone claimed that would... Wait, what? Wait, what? Wait, what? The inverse Galois problem asks whether every finite group can be realized as a Galois group of some finite extension of Q. Uh-huh. It is still open, right? Which means we don't know if it's true or false. Agreed. So if someone claimed that Q8 cannot be realized over Q, that would not falsify IGP. What?
Yes, it would. Yes, it would. I mean, yes, it would. That's exactly what it would mean. That's exactly what it would mean. Um, yeah. It can be realized as a Galois group over Q. Okay. Wait, am I crazy? Did I misread what it said earlier? Uh, oh, cannot be realized as a Galois group over Q. I mean, there you. Yeah. Okay, but now it's changing its tune. Uh, gives an explicit polynomial. Earlier literature sometimes claimed non-realizability, but those applied to embedding problems or regular realizations. Okay, so I think we know maybe why the AI was getting confused then. So I know. Wait, did it say something about embedding problems, or what was it saying? No, I mean, there's really no other way. I mean, it says due to embedding problems, but yeah. Whose Galois group is isomorphic to the Latrinian group. Um. Oh, and then now, wait, it's changing its tune one more time. So your intuition is spot on. If a finite group truly couldn't be realized and IGP claimed all can, then IGP would be false. Okay. So it corrected itself in the end, but a lot of internal consistencies here. It highlights a key theme, distinguishing between obstructions that are genuine versus apparent constructions. Okay. No problem moving on from the discriminant question. Just to note, the discriminant being a square. Wait, did we say something about the discriminant? Okay. Wait, did it ask me something about the discriminant? Oh, I guess it did. Why do you think the discriminant of this being a square forces the Galois group? I mean, that's kind of a weird question. Why do you think that is true? I don't know. That's a technical question, kind of, isn't it? Well, mind you, I mean, it is true, so maybe it's not a terrible thing to set someone on the path of trying to sort that out. Yeah, okay. Would you like to extend the session briefly to see how rigidity works, or shall we conclude and dive deeper into Galois theory foundations next time? Well, message completed, lesson completed. So let's go. Let's take a look at the course. So we've completed that lesson. I should say in this one also, it didn't really. This one kind of bugged out again. It just said everything. Said the same thing for every one of these lessons. So I don't know. Let's just click a random one and see what happens. While it's loading, we can go learn some more Galois theory. We can go learn about rigidity. Right, we have our fundamental group, definition. I hope I didn't kill your ears. I'll try to remember to edit this part out. Right, just some general stuff about deck transformations, Galois coverings. I mean, all important stuff to remind yourself if you're reading this document. Punctured sphere. Yeah. So we have some theorems about
have some theorems about these things. Let's see, Math Hub loading. No. Sorry, it is loading, but it is not loaded. Ideal points. Okay. The ideal points are equivalence classes of tilde defined on the circular components. So the number of ideal is equal to the number of components. Show me the Galois theory. So this is just, I guess we're just proving the claim about the generators by taking these generators around each puncture. Proof is omitted due to the length. Well, fair enough. Fair enough. The fundamental group of this is freely generated by these. Yeah. Oh, this is okay. Welcome to session 16. Okay, we're at the end now apparently. So let's see what it has in for us for session 16. By now we've explored a wide range of techniques realizing finite groups as Galois groups over various bases, space fields, but most importantly, but also those. We've also learned how these methods might extend to new cases. Right. This raises a question. What allows these to succeed? For instance, rigidity works for PSL2P, but fails for many P groups. Meanwhile, embedding problems are powerful for solvable groups. Can you identify one group we know is realizable over Q? I would hope so by session 16. Okay. Let's check one in the middle to see what it would have said. Just somewhere in the middle here. Yeah, like let's see what's going on in session 11, I wonder. It was Hilbert who first systematically approached the inverse Galois problem. Of course he did. And his ideas still form a crucial role in the functioning of the rigidity method. His main idea allows a Galois group over the rational function field to be realized as a Galois group over Q. This chapter explains Hilbertian fields. So we take a finite extension. We let these be algebraically independent. What can we say about this? An FG extension as above. Then this has isomorphic Galois group. Makes sense. Makes sense enough to me. Still loading. And then I guess this will be true. By the Galois correspondence, we see any intermediate field between these is of this form. Right. L is said to be regular over K if K is algebraically closed in L. Wait, what? What? What does that mean? What does that mean? Maybe it is getting late in the day for me because this doesn't make any sense to me at this point in time. Okay, welcome to session 11. So far we've focused on realizing Galois groups over Q. Today we shift perspective to function fields. Okay, cool. This setting offers a striking contrast where the inverse Galois problem remains open in general. Over many function fields, it is completely solved. Let's begin with the basics. The IGP over a field K asks, does every finite group occur as the Galois group of some finite extension? Yeah. Such extensions correspond geometrically to branch covers of the projective line. If the extension is regular, meaning it's linearly disjoint from the algebraic closure of K, not sure what that means, then the cover is geometrically connected, and the Galois group is called the geometric Galois group. For example, over C adjoin T, the IGP has an affirmative answer. I think that's in a Luffy too, actually. Every finite group appears as a Galois group of a regular extension, which follows from Riemann's existence theorem, which links finite covers of the Riemann sphere to permutation representations of the topological fundamental group. So I think we're seeing a bit of that in this random WordPress document. In algebraic terms, this means there exists a Galois cover with that Galois group. Now consider a finite field. Here the situation is more subtle because the constant field is not algebraically closed. Yeah. Obtained by extending field of constants. Extensions. Right. I see. Genuinely geometric. Right. So the IGP over this focuses on regular extensions to avoid trivial constant field enlargements. A natural question arises, what finite groups can be realized as Galois groups of regular extensions of this? This leads directly to Abjankar's conjecture. I've never heard of this, actually. Which precisely characterizes the realizable groups in terms of their quasi-P structure. Next up, we'll explore Abjankar's conjecture in detail, how ramification constraints in positive characteristic restrict, and why this doesn't happen over CT. Great. Let's hear it. But actually, I do have a question about but first, can you please explain what it means to be linearly disjoint from the algebraic closure? And then we'll probably end it off for today. I gotta edit all of this. Sort of. I don't need to edit all of this, but I'm probably going to edit at least parts of these videos. There's more interesting parts to this and less interesting parts to this. Yeah. Like this part right now. This document is substantial, and I'm realizing that it would take quite a bit of work to understand, to go through the rigidity method. Although surely there's maybe a more direct thing. Let's look at this 45-page one. Yeah. Okay, rationality and rigidity begins over here. Let's go look at rationality of conjugacy classes. We say a class is rational if any irreducible character takes a rational value on there. Okay, cool. So for the symmetric group, everything is rational. Definitely not the case for, say, the cyclic group of order P, though. Not in general. Not every... Yeah. I mean, the identity... I guess everything else will have some... Yeah, for Z mod P. I think everything else you could cook it up. Well, if P is bigger than 2. P is bigger than 2. Or, I'm trying to think. Yeah, I think as long as P is bigger than 2, you could always cook it up. So you've got a non-rational character. Primitive mth root of unity for any element in the Galois group. We have that if this is an irreducible representation. Oh, this is interesting. If we have an irreducible representation, then precomposing that irreducible representation with... Wait, what? What is sigma? With an element of the group? Huh? What does that mean? Oh, I wonder if this is precomposition by conjugation by that element. Then this too is an irreducible representation. That would check out. And if the irreducible character afforded by this is chi, then this is this precomposed with chi. That would still check out if this means if it means precomposing with conjugation. But I don't see anything here that is specific to this Galois group. Yeah. I mean, this is true of any finite group, actually. The conjugacy class. A conjugacy class is rational if and only if... that class to its power... to n is itself for any n and m relatively prime. That's kind of cool. Okay, but we're back here. Excellent question. Let's clarify what it means for a field extension to be linearly disjoint from the algebraic closure of the base field. The key is to distinguish geometric extensions from constant ones. So suppose K is this, and let L be a finite extension. I get what it's saying now. Okay, but let's read the explanation. Let K bar denote the algebraic closure. We say that L is linearly disjoint from K bar over K if the natural map... Oh, this is not exactly what I was thinking, but I understand the spirit of it, I think. If this tensor product map is injective, I see. Equivalently, an isomorphism onto its image. Right. In more concrete terms, this means that no non-trivial k-linear relations exist among the elements of L. I see. So this is what I was talking about before, avoiding the base field extensions. When this is Galois, it's equivalent to saying that the intersection is K. Right. That is, the only elements of L that are algebraic are over K are already in K itself. That's a regular extension. Okay. Makes total sense. Why does this matter? Because if we allow arbitrary extensions, we could trivially realize any finite group. Well, is that true? By taking a Galois extension M over K with Galois group G. Oh, if one exists. Okay. Yeah, so you're lifting from the problem over the base field. Yeah. But this doesn't reflect geometry of the projective line. Yeah. Right. Now to connect back to our session objectives. Thank you. It's nice that it kept me on track. The IGP over function fields like KT is often easier over Q because we can use geometric tools. Over Q, we lack a basic base space like P1, and ramification is far more rigid. Unless maybe we have the field with one element. I don't know if that would actually help. With that clarified, are you ready to dive into this? Yes. Amen. Okay, and yeah, it verified a bunch of stuff for us, so cool. Okay, so it finally loaded. Great. Since you're ready to dive into Abyankar's conjecture, the central result that characterizes exactly which finite groups can be realized as Galois groups. Finite field characteristic P interested in regular extensions. Formulated 1950s and only proved in 1990s. Wow. For the affine line, what does that mean? And Harbader in full generality. A finite group occurs as a Galois group of a regular extension of KT if and only if it is quasi-P, meaning that the subgroup of G generated by all of its elements of P power order is the entire group. Interesting. For example, the symmetric group in characteristic 2, the two elements generate all of 3. Well, all the symmetric groups are generated by their two elements. So all the symmetric groups should be realizable over F2T, right? In contrast, a cyclic group of order L not equal to P is not quasi-P since it has no non-trivial P elements. That is a cool theorem. This is strikingly different from the situation over CT, where every finite group. Yeah. Over Q by contrast, we don't have such flexibility. Okay. It's getting a little repetitive with that point. While many groups are known to occur, yes, okay, we know, it remains open. So to summarize, all finite groups occur regularly. Here, only quasi-P groups. Okay. Okay. So I've been recording for like well over an hour now, and I'm probably going to cut a lot of this material out. So what do I think? Well, overall, I would say, if I had to sum it up in one noise. But there's pros and there's cons. There's pros and there's cons. There's things I like and there's things that aren't great. The obvious thing that wasn't great was the sitting around and waiting, right? So that wasn't really fun. And when I had to, as I was waiting for it to load, like, as you saw, because I'm sure you watched everything, you didn't just skip here from the start of the video. There was, I went to Google and I looked at Google and I went to Claude and I played around with Claude, and I did a bunch of learning. And so it seems like it's just so much faster to learn in a more traditional way, to learn from a textbook, or to use like random PDFs or Claude or something like this, Stack Exchange, whatever. Of course, using Claude isn't great, so we'll talk about that in a second. But so those parts weren't fantastic. Although you could say, well, I'll pair using MathHub, understanding that it's slow, with reading extra stuff and just be like, make use of your time, right? Don't just sit there picking locks like I did in the first section, like I did in the inverse Galois theory problem. Go read other PDFs and stuff in that time. So why would you, is it weird if I adjust the mic volume in the middle? Why would you use MathHub then? Well, probably the really coolest thing about it is that it verifies things in lean. That is so cool. That's what's slowing it down, unfortunately, is it's verifying things in lean. But that's awesome, right? Because then it's like, wow, you can not only
have some extra trust that you can't have with other AIs. With Gauss. Is that what this thing's called? I don't remember what the AI is called, but you can also go and click and see. Even it'll tell you, like, you can go see the lean code that it like wrote and checked. So that's crazy. That's crazy. However, that being said, um, it also still got things wrong because, like, not absolutely everything gets coded in lean, and not everything can actually compile in lean. So the thing is, there was, if you look in the Galois theory part, there was a little section where it said something that was straight up false, right? Like, it contradicted itself. The inverse Galois problem is a famous open problem about realizing Galois groups, and it told me that the quaternion group couldn't be realized as a Galois group, which is just totally false. So it's not perfect. You can't put all of your trust into it, even though it has this like lean code baked into it. So that's another thing to be mindful of. But overall, like, I think it's cool. I think it's definitely a cool experiment. Will I personally continue to use it? Probably not. Probably not. I mean, I've got a bunch of tokens for it, so um, I could, yeah, reasonably still use it. I'll let you guys know if that happens, but I'm not so sure that I will. Should you use it? Should you use it? Well, the thing is, to be honest, I don't know how much it cost. So I don't know. And I guess even if I did, I couldn't really tell you because, my financial situation is probably different than yours. Probably worse because I'm a grad student, but maybe better because maybe you're an undergrad. I don't know. Um, so yeah, that's something I can't really answer anyways. Again, I personally don't think I'm gonna use it at this point, but I do think it has value. So it's maybe worth going and checking out. And that's pretty much all I have to say. So thanks for thanks for being here, and QED.